Nuclear fusion, the process of combining atomic nuclei to release vast amounts of energy, has long been regarded as the holy grail of clean and limitless power generation. Unlike nuclear fission, which is currently used in nuclear power plants, fusion does not produce long-lived radioactive waste or carry the risk of catastrophic meltdowns. In addition, fusion fuel is abundant and widely available in the form of hydrogen isotopes. The fusion process occurs at extremely high temperatures and pressures, similar to those found at the core of stars. By heating a mixture of hydrogen isotopes to millions of degrees Celsius, the atoms become ionized and form a hot plasma. In this state, the positively charged atomic nuclei overcome their natural repulsion and can come close enough together for the strong nuclear force to bind them, releasing a tremendous amount of energy. One of the most promising fusion reactions is the fusion of deuterium and tritium, two isotopes of hydrogen. This reaction releases enormous amounts of energy, primarily in the form of high-energy neutrons. These neutrons can be harnessed to heat surrounding materials and generate steam, driving turbines to produce electricity. The fusion reaction itself produces helium, which is harmless and non-radioactive. Several approaches have been pursued to achieve controlled fusion on Earth. One of the most well-known is magnetic confinement fusion, used in devices called tokamaks. Tokamaks use powerful magnetic fields to confine the hot plasma and prevent it from touching the walls of the reactor. By carefully controlling the plasma and sustaining the necessary conditions for fusion, scientists have made significant progress in achieving controlled fusion reactions in tokamaks. Another approach is inertial confinement fusion, which uses lasers or particle beams to rapidly compress and heat a small pellet of fusion fuel. The intense pressure and temperature generated by the compression cause the fuel to undergo fusion. This approach is being studied in facilities such as the National Ignition Facility, NIF, in the United States. While significant challenges remain, such as sustaining the necessary temperatures and pressures for long periods and finding suitable materials to contain the plasma, the progress in fusion research has been remarkable. International collaborations, such as ITER, International Thermonuclear Experimental Reactor, are working towards building a large-scale tokamak that aims to demonstrate the feasibility of fusion as a viable energy source. The potential benefits of nuclear fusion are immense. Fusion reactors could provide a nearly limitless supply of clean energy, reducing dependence on fossil fuels and mitigating climate change. Furthermore, fusion fuel is abundant and can be extracted from seawater, ensuring long-term availability. The development of fusion technology could revolutionize the energy landscape and address the pressing global need for sustainable and clean power generation. In conclusion, nuclear fusion holds the promise of providing safe, clean, and virtually limitless energy. Through ongoing research and technological advancements, scientists are working to achieve controlled fusion reactions on Earth. If successful, fusion could usher in a new era of sustainable energy and contribute to a greener and more prosperous future for humanity.